Mr. Commissioner, Callan, C-A-L-L-A-N, initials T-E, appearing on behalf of Her Majesty the Queen and Ray, the Province of British Columbia. I expect my examination will be 60 minutes. Mr. McDonald, you would agree that water quality conditions and freshwater habitat are likely not the primary factor influencing sockeye salmon productivity in the study area?
Yes, that's correct.
Okay. You would also agree that you did not find a dramatic change in the water quality or levels of a particular contaminant on the out-migration in 2007 or on the in-migration in 2009 that would explain the low number of sockeye in 2009?
That's correct.
It would have been a useful exercise, though, to conduct this research. Sorry. And specifically, when you looked at all of the concentrations, all of the contaminants of concern identified in table 513 to 517, you observed that all of them have the same concentrations or lower levels than they did in 1990. And specifically, if you could turn to page 66 of your report, and it would be the second paragraph, midway through, where it says, however, comparison of the results for the entire watershed for the two time periods revealed that the frequency of exceedance of the toxicity reference values either remained the same or decreased for all contaminants of concern, table 513 to 517. Such patterns of decreasing or constant frequency of toxicity reference value exceedance over time are also generally evident across all areas of interest.
There was a lot of information in that question, and maybe we need to break it up a little bit so that we don't provide incomplete information.
Okay. Would you agree that all of the contaminants generally had the same or lower levels than they did in 1990?
So you referenced tables 513 to 517. Those don't provide information on concentration specifically. What they identify is the frequency of exceedance of the toxicity thresholds. So they don't provide comparisons of pre-1990 to post-1990 concentrations.
Okay, however, the frequency then of exceedance was generally lower after 1990 than before 1990.
I'm just looking at tables. Why don't we go through the tables one at a time? Do you want to start with table 513, which is T126?
Well, I guess rather than do it on a graph-by-graph basis, because I do have limited time, do you agree with the statement that you made at page 66?
Sorry, once again, could you restate that portion of page 66 that you're referring to?
Okay, it's the second paragraph of page 66. However, comparison of the results for the entire watershed for the two time periods revealed the frequency of exceedance of the toxicity reference values either remained the same or decreased for all contaminants of concern, table 5.3 to 5.17. Such patterns were decreasing or constant frequency of toxicity reference value exceedance over time were also generally evident across all of the areas of interest.
Yeah, and that's a general statement. When you look at the details, you'll find exceptions to the general statement. So, for example, if you look at, total iron, for example, in the South Thompson region, you'll see the incidence of, for the frequency of exceedance of the toxicity threshold is higher in the post-1990 period. There's a variety of exceptions to that general statement, but overall, that was the conclusion, yes.
What is a toxicity screening value?
Toxicity screening value for the purposes of our report is a conservative toxicity threshold. It's a concentration below which we expect to see a very low probability of observing adverse biological effects, and above which there is some increasing probability of observing effects as the concentrations increase.
And what is toxic concentration low?
I'm sorry?
Do you know what the toxicological term toxic concentration low means?
I think maybe you need to point me to some reference for that. I don't know specifically what you're referring to.
Okay, do you know what is meant by lowest observable toxicity concentration?
Generally, in toxicological studies, the term we use is lowest observed effect concentration or lowest observed effect level. That's a more common term than I think the terms that you're using right now.
How does toxicity screening value compare with lowest observed effect of toxicity?
So it's lowest observed effect level is the term that I used previously. Sorry to have gone quickly over that. Typically, in a toxicological study, an experiment will be done on, for example, sockeye salmon, where you will expose a fish to various concentrations of a contaminant in water. You will, and typically if you can sort of picture beakers with water in each one of them and different concentrations of the contaminant in each one of those beakers, you'll be able to look at the effects that you're trying to observe in each of the beakers. And your first beaker is typically your control, and then your next beaker is a relatively low concentration, and concentrations increase as you go through the progression. What you often do in a toxicity study is you report the concentration at which there was no adverse effects on the organism. That's the no observed adverse effect level. And then the next concentration tested above that is the lowest adverse effect concentration or level. So typically that is reported for individual studies rather than, or individual experiments rather than, what we've tried to do is take information that integrates information from a wide variety of experiments into something that we call a toxicity screening value. So we consider variables like, or reported results like lowest observed effect levels or no observed effect levels in the literature, integrate those across a variety of toxicity tests and species, life stages, et cetera, that have been tested. And then that gets us to a point where we can select a toxicity screening value, which we believe is very protective of aquatic organisms. And that's the ones that we've selected in this case for the purposes of doing the assessment in Chapter 4.
Has a lower contaminant concentration.
Again, a lowest observed effect level is from an individual study. And so you might have in the literature lowest observed effect levels reported for sockeye salmon eggs or sockeye salmon, alevins or fry. You would also have lowest observed effect level reported for other fish species, invertebrates, etc. So when you describe which is a lower observed effect level, you need to keep in mind that what is reported in the literature is hundreds and hundreds of, for example, lowest observed effect levels for a substance like copper or cadmium, which is very well studied. And then how does that compare to our toxicity screening value? We would expect if the Canadian Water Quality Guidelines were designed and developed in the way that they're intended to be, that the toxicity screening value would be lower than most or all of the lowest observed effect levels reported in the literature.
Okay. Do you have any idea of the magnitude of the difference between the two numbers?
And again, there's no such thing as a single lowest observed effect level. So there's not two numbers that are compared. There's multiple numbers that are compared to a toxicity screening value. So it's important to keep that in mind.
Okay, for my purposes, when we're talking about the lowest observed effect concentration, I'm speaking specifically with respect to sockeye salmon. Can you then outline the order of magnitude or the multiplication factor between the toxicity screening level and the lowest observed toxicological effect?
What you're describing is I think, possible conceptually, and that's the way I will answer your question. But again, practicality is important as well, because again, we're talking about hundreds of contaminants and there is no single ratio between the toxicity screening value and the lowest observed effect level for sockeye salmon. It's because there's so many different chemicals that have been tested, and in many cases there may not be an LOEL for lowest observed effect level for sockeye salmon. And so what it sounds like you're looking for is a very specific number, which I can help you with if you want to get very specific about individual chemicals, and if we want to look at the underlying data, we can certainly do that. But I don't think that's really what you're looking for, and I think what you're looking for is a more conceptual answer. And so to get to a conceptual answer, you look at the protocol that is used to develop things like the water quality guidelines. And typically what is in that protocol is that rather than a lowest observed effect level, there's several techniques for developing these concentrations that are protective of aquatic organisms. One of which is looking at the median lethal concentration. That's the concentration of a contaminant that is toxic to half of the animals that were exposed, and multiplying that concentration by a factor of 0.1. So it's a 10-fold safety factor for a median lethal concentration. That's not an LOEL, though. That's not a lowest observed effect level. There's a different protocol for developing from a guideline from an LOEL. Is that what you were looking for? Is that kind of a conceptual answer?
No.
Okay.
What I'll ask you then is, you're saying then that the lethal concentration 50 is 10 times the lowest observed effect level. Is that how you're
No,
evaluating this?
that's not what I'm trying to say. And I'm sorry if I'm not being clear. The Canadian Council of Ministers of Environment, they're the organization that is largely responsible for developing water quality guidelines in Canada, with support from the various provincial agencies as well. And they work as a team in this process. And to guide that process, they've developed a protocol for developing water quality guidelines that will be protective of all species and all of their life history stages over indefinite periods of exposure. And so this protocol then provides a basis for calculating a water quality guideline, not a lowest observed effect level, but a water quality guideline from a median lethal concentration. That's that LC50 concentration that is typically reported in the literature, or from a lowest observed effect level. There's also a basis for calculating the guideline from that tool as well. And so I may or may not be helping here, but I'm trying to make sure that we use the language clearly enough so that we know what we're talking about.
So it's fair to say then, for all of your screening values, they are the toxicity screening values. They are not the lowest observed effect concentration or level.
Yes, so the protocol calls for for developing a guideline that is lower than the lowest value that is reported in the literature. That's not 100% true of all the water quality guidelines. Some of them were developed prior to when the protocol was in place, and so there's more recent data that demonstrates effects at concentrations lower than the guidelines in some cases. But generally speaking, that statement is correct.
So all of your numbers then that you've had for measuring contaminants, if you look at the numbers and there's an exceedance of the toxicity screening value, it doesn't mean that necessarily that the sockeye salmon have observed or have experienced any toxicological effect.
Yeah, and I hope, as I described this yesterday in when we talked about Chapter 4, the use of the toxicity screening value was intended to provide a basis for identifying the contaminants that do not pose risk to sockeye salmon. And when those values are exceeded, then we have a situation where we have chemicals that pose a potential risk to aquatic organisms, is the way I think we phrased it in Chapter 4.
But when you do go into Chapter 4 as well and do the enhanced screening, you still aren't comparing the effects of the lowest observed effect concentration as well. You're looking at the 95 percentile number instead, and the toxicity screening value.
Could you ask that question again, please?
When you're doing your enhanced screening, once you identified the contaminants that were potentially of concern because they exceeded the toxicity threshold at some point in the province when you looked at the highest number anywhere, you still didn't look at the lowest observed effect concentration. You looked at the toxicity screening value, again, in the 95th percentile.
No, that's not correct.
What did you do then?
So, and I think now you're referring to the work that was done in Chapter 5.
That's right.
Okay, so the two main differences between what happened in Chapter 4 and what happened in Chapter 5 is, we use that analogy of the sieve, where we had a very tight screen in Chapter 4, and only the substances where we had a very high level of confidence that they would not pose adverse risk to aquatic organisms were the ones that dropped away through that screen. Everything else was retained on top of our sieve. So in Chapter 5, what we've done is we've widened the mesh, if you like, on that screen in two ways. So one you appropriately identified was rather than using a maximum concentration of each of the chemicals of potential concern, we looked at the 95th percentile concentrations of the chemicals of potential concern. But then, in addition to that, rather than using a toxicity screening value, as was done in Chapter 4, we've used something called a toxicity reference value. And this is where we've tried to identify toxicity thresholds for sockeye salmon specifically. That wasn't possible. We developed those for salmonids. And the idea was to identify the concentrations of each of the individual contaminants of potential concern below which there was unlikely to be adverse effects on sockeye salmon or other salmonids that have similar sensitivities, and above which there is a likelihood of observing adverse effects. So it was a very different tool that was used to evaluate the concentration data in Chapter 5 than what was used in Chapter 4.
Observed effect concentration.
It would be more or less equivalent to a lowest observed effect concentration, the toxicity reference value.
For your report, you measured approximately 200 contaminants of concern.
Yes, that's correct.
Okay. How did you measure them? Specifically, did you take samples of water and analyze them, or did you measure effluents from the surrounding areas?
I think, as I described yesterday, we relied on pre-existing data that had been collected and compiled in the case of the water chemistry data that had been compiled in the provincial EMS database.
And there were some chemicals that you didn't have data for, and you used pesticide sales data.
Could you ask that question another way, please?
Were there any chemicals that you've purported to measure concentration levels on that weren't from actual measurements that were observed through water samples?
Yes, not in the way that you've just characterized it, but yes. And the one example of that was some estimates of tetrachloride dibenzodioxin toxic equivalents for sockeye salmon roe for 3 stocks, upriver stocks. And what we used was the estimates or the predictions in the De Bruin et al. Paper 2004.
Okay, we can get to that.
So those were the predicted concentrations, but I don't believe that for either water or sediments we predicted concentrations of anything.
Did you at any point do a comparison of contaminant concentrations in 2007 or 2009 in comparison to other years when sockeye salmon returns were good?
In 2007, 2009, yeah, we looked at those data, absolutely, to see if there was any patterns that we could discern. We also looked for spills that potentially had been reported in the river.
And what were your findings?
We did not see anomalous results, meaning anomalous meaning well outside the general population for the post-1990 data for either of those 2 years.
If you could turn to table A3.1, which is page 26 of the appendix, would you agree that many of these samples are very old?
As I review the information in this table, what I see is that the period of record ranges from 1965 to 2010, and I think that's what I testified to yesterday as well.
And you would agree that in many of the areas of interest, you did not have data that went to 2009 or 2010?
Yes, I would agree that in I don't know what percentage is offhand. We could calculate that if you would like, but there were numerous areas of interest where the period of record either ended in 2008 or before that. Yes, that's correct.
And certainly the Chilko River area of interest, the latest date that you would have had for that sample was June 2004. And that would be somewhat representative of some of the areas.
That's correct for Chilko, yes, but representative of other areas. Can you be more specific about that?
For instance, the Pitt River area of interest.
Yes, I see that for Pitt.
Okay.
Did you want to go through this list? I just don't want to mischaracterize 2004 being the latest date for most of the areas of interest, because I'm not sure that that correctly characterizes that.
Which areas did you feel that you had significant and updated information from then? We'll go at it that way.
Could you state that question another way, please?
Which ones of the areas of interest were you comfortable with the updated nature of the water samples?
So, I'm going to back up just a little bit here and say we're talking about the temporal coverage of the data right now, and I think that's a very relevant discussion as well. Even more relevant than the temporal coverage is the spatial coverage of the data. And I think I talked about that at some length yesterday, where I indicated that I was relatively dissatisfied with our ability to characterize particularly conditions in incubation areas throughout the Fraser River Basin and in early rearing areas throughout the Fraser River Basin. So those are two key data gaps that I think we as we talk about data in more detail, we need to keep sort of that big picture in mind. Now getting back to the temporal coverage, would we have liked to have had data for the whole period of record for each of these locations that we did have data for? Absolutely, we would have wanted to have that. And are there some of these areas of interest where there is incomplete coverage in the most recent years? Yes, I would agree that that's the case.
And the province did have paper data that was available, but it was excluded for the purposes of your report due to time constraints.
That, I don't remember that specifically. I believe that to be true, but I don't specifically remember exactly what was available in paper copies that we were not able to access because they were not available electronically.
Can you define bioavailability?
Bioavailability is a measure of how accessible, in the context of contaminants, how accessible a contaminant like, for example, cadmium is to an organism that it is exposed to. So how likely that animal is actually going to experience that exposure of that contaminant in the form that it's in the environment.
Now, for the purposes of your report, you assumed all of the chemicals were bioavailable for sockeye salmon to consume.
That's not exactly correct, no.
Okay, if we could turn to page 57 of your report. And in particular, it's the first paragraph under 5.1, and it's the last sentence. Furthermore, it was assumed that 100% of the measured concentrations of the chemicals of potential concern were biologically available, which is unlikely for total metals in surface water that carry substantial suspended sediment loads. Do you disagree with that statement?
No, I agree with that statement. Your question was bioavailable to consume, and that is what threw me for a loop. I didn't understand what you meant by that. Again, bioavailability is a measure of how accessible the contaminant is to an organism in its environment. In this particular discussion here, we're talking about contaminants that are associated with the water column. The sockeye salmon aren't going to consume those contaminants. They're going to take those up via their gills or via contact with their epidermis or their skin, essentially. Those will be the two main mechanisms by which they'll they'll access contaminants in the water column. When we talk about bioaccumulative contaminants, then we talk about consumption of contaminated prey items, and then we can talk about 100% bioavailable to consume. In that case, that becomes more relevant. But in the context in which you ask the question, that's why I want to make sure that we're talking about the same things when we're having this discussion.
Okay. Well, if you assume that I do not use the word consume and that I use the word consume or absorb through water, would that statement that I made earlier be correct?
Yes.
Okay. Now, this is an unrealistic assumption. Do you agree?
Well, and as you see in the last part of this sentence, it says which is unlikely for total metals. So it may be for things like phenols, for example, which are largely going to be dissolved in the water, it's a very realistic assumption. But for certain things like metals, which can be either dissolved in the water column or associated with the particulates, like the suspended sediments in the water column, it's unlikely that 100% of the metal load is going to be biologically available.
So with respect to metals, it would overestimate the results.
It would either estimate the results correctly or it would overestimate. It would be one or the other. If in some situations, for example, in the rearing lakes where you have very clear waters, estimate of 100% bioavailability of metals may be very reasonable. In the main stem Fraser, where you have hundreds of parts per million of suspended sediments, it's unlikely to be correct. So it's it's not one or the other. There's a variety of different conditions that exist within the Fraser River Basin, and we need to consider that range of conditions when we make generalities about it.
Are you aware of any scientific studies which evaluate the amount of bioavailability of metals?
Yes, I am.
Did they estimate a percentage that were bioavailable compared to the concentration?
Well, I've done a number of studies in a variety of different places across North America that have been directed explicitly at answering that topic about metals, yes.
Were any in the Fraser River Basin?
No, none of them were in the Fraser River Basin.
Where were they?
Places like the Tri-State Mining District in Oklahoma, places like the Calcasieu Estuary in Louisiana, places like Newark Bay, New Jersey, those kinds of places around the U.S., Superfund sites typically.
In those sites, what percentage did you find that were actually bioavailable?
There is no single answer to that question. There is a range of answers. I look primarily at metals in sediments and their bioavailability. That's one of my focus areas. And we find that we use an estimate of about 70% bioavailable for metals in sediments. For across North America, just looking at averages for a variety of different sites that we've actually done this work at.
Now, did you do any that were water specific as opposed to sediment specific?
Yeah, and for water specific, the range would be even greater than for sediments because of the issue we just brought up. In clear waters with low levels of suspended material, up to 100% of those metals are either present in the dissolved form or as in fine colloids, which are highly available. Both of those forms are available to the organisms. So in those kinds of situations, you would see 100% or close to 100% bioavailability. In other situations where you have high levels of metals that are associated with suspended solids as well, the percent bioavailability would be much lower. And I can't give you a specific answer for that, for what that might be.
Could you estimate the range at the lower end?
The range is from at the lower end probably. I don't think I could.
For the purposes of your report, did you assume that salmon were swimming and eating in the top 15 meters of water in the ocean?
My report was focused on freshwater habitats in the Fraser River, so I didn't look at ocean habitats at all.
Would you agree with the following definition for bioaccumulation? The key elements of bioaccumulation are that a fat-soluble or lipophilic chemical is ingested by a species at the bottom of the chain, the food chain. Many of the bottom trophic level specimens are eaten by another animal at the middle trophic level, and then a predator eats a number of the middle trophic level, and the lipophilic substances magnified through consumption. Do you agree with that definition of bioaccumulation?
I would use the definition that you gave is one of biomagnification rather than bioaccumulation. And biomagnification is a type of bioaccumulation as well. But bioaccumulation is just simply the process whereby contaminants in the environment find their way into organisms and accumulate in their bodies.
Would you agree that sockeye salmon are in the middle of the food chain, and specifically when they're smolts?
In the middle of the food chain, I think what you're asking is, or what you're trying to get at is, are they at the highest trophic level? Are they top level consumers? And the answer is no, they're not. They're typically planktonic feeders, and so they're somewhere below the top level of the food chain. The term middle of the food chain is not a very specific term. It would. There are ways of identifying where various organisms are within a food web, and I guess one could use the term middle if you choose to.
Because the smolts are in the middle of the food chain, or are planktonic feeders, bioaccumulation is not really an issue for sockeye salmon in the same way that it would be for killer whales or harbor seals.
Those animals at the top of the food web are the ones that are going to accumulate the highest concentration of those bioaccumulative substances. That's absolutely certain. One shouldn't say that because they don't accumulate contaminants to the same levels as seals or killer whales, that bioaccumulation is not an issue for sockeye salmon. I think that would be an incorrect inference. But yes, you're right, they would not accumulate to the same levels.
And the fact that sockeye salmon only live for 4 years would also be a mitigating factor against them being highly affected by bioaccumulation.
No, that's incorrect.
Are you saying?
Would you like to know why?
Sure.
Well, typically bioaccumulation is evaluated using something called bioaccumulation tests. That's how we do it in the laboratory. And for most of the substances that we look at, things like PCBs, things like DDTs, things like dioxins and furans, these bioaccumulation tests are typically run, and I'll refer to sediment bioaccumulation tests because those are the ones that I run most frequently, or have run for me most frequently. We run those for 28 days. With those 28 days, we'll often run something called a 56-day time to equilibrium test as well. And that's to determine how close to equilibrium we've come within that 28-day exposure period. And what we find is for most contaminants, we see them coming to steady state in the tissues of the organisms that we're exposing within about 80% of steady state within 28 days. And typically by 42 days, you hit maximum concentrations in those organisms. And so an organism that lives 4 years, when you put it in perspective of coming to steady state and largely to steady state, 80% of the way to steady state in 28 days, 4 years is a very long time in comparison.
Now, for your report, you would agree that you didn't have access to any sockeye salmon-specific, salmonid-specific, or fish-specific sediment quality guidelines in the academic literature?
Could you restate that whole, I'm sorry, I was expecting that question to go a different way. Could you restate it, please?
Would you agree that you did not have available to you any sockeye salmon-specific, salmonid specific or fish specific sediment quality guidelines?
I don't think I would agree with that statement. And in the interest of time, I'll explain quickly why that is. We relied upon the consensus-based sediment quality guidelines that our group developed with the U.S. Geological Survey back in 2000, the year 2000. And they were based on effects on sediment-dwelling organisms. But we have also evaluated how effectively those sediment quality guidelines predict adverse effects on fish as well, exposed to sediments. And what we find is that they do a very good job of predicting effects on fish. And the fish that we use here were not sockeye salmon. We use fathead minnows in that evaluation. But they were good predictors of toxicity, and so although they were not developed specifically using data on sockeye salmon or fish, we find that they work very effectively for predicting effects on fish as well.
Okay, so then you would disagree with the statement in paragraph 1 of page 61 that says sockeye salmon specific, salmonid specific, or fish specific sediment quality guidelines were not located in the literature to support the detailed evaluation of sediment chemistry data for the Fraser River Basin?
No, I'm not disagreeing with that statement. What I'm saying is that although we didn't have guidelines that were specifically developed using data on toxicity to fish, we have subsequently evaluated those sediment quality guidelines and find that they are predictive of toxicity in fish. So the statement is correct as presented on this page of the report, but I wanted to provide you with that supplemental information so that you would understand that these tools, although we haven't evaluated them with any of the salmonids or sockeye salmon, we've evaluated them with fish species, and we find that they're predictive of toxicity.
So if we could turn to page 3 of your report, or page III. In your report, you wrote, nevertheless, the concentrations of selenium and 2378 tetrachlorodibenzoedioxin toxic equivalents occurred or are likely to have occurred in salmon eggs at concentrations sufficient to adversely affect sockeye salmon reproduction. I put it to you that you do not have adequate data to support that statement. Do you agree or disagree?
Occurred or likely to have occurred, and I think where you're getting at here is the De Bruin predictions of 2378 TCDD toxic equivalent concentrations in the eggs of fish using the model that he developed. I see I'm getting ahead of myself. I will wait until you get there.
You are. So when you're saying 2378 tetrachlorodibenzoedioxin, you don't actually mean specifically 2378 tetrachlorodibenzoedioxin. That's correct, right?
Well, I believe the whole statement is 2378 tetrachlorodibenzoed-p-dioxin toxic equivalents.
So the answer is yes, then. You don't actually just mean that one particular compound.
Yeah, and so the toxic equivalents, I think we talked about those a little bit yesterday as well, and what the toxic equivalents allow us to do, because there are up to 209 individual congeners for 210 individual congeners for the dioxins and the furans, the chlorinated dioxins and furans, and they have similar modes of toxicity. And because there are a number of PCBs that exhibit the same types of effects as the dioxins, there's 209 of those. PCBs, a subset of those, the coplanar PCBs are the ones that exhibit dioxin-like effects. This tool of toxic equivalence allows us to evaluate the additive toxicity of all of those different compounds together. So it provides a mechanism for looking at the additive toxicity of multiple dioxins, furans, and PCBs that have the same or very similar modes of toxicity.
Okay, so it's a cocktail as opposed to one particular compound.
Correct.
And that would be because 2378 tetrachlorodibenzoed-p-dioxin has never been commercially available in Canada.
I'm sorry, I didn't understand your question.
The question is 2378 tetrachlorodibenzo-P-dioxin has never been commercially available in Canada.
Do you mean available for purchase in Canada?
That's right.
I doubt that that's correct, but I think what you mean in quantities that could be used in industry and then released into the environment rather than you purchased for the purposes of doing studies on that particular substance. Is that what you mean?
Okay. Well, what I mean is commercially available, as in not available for scientists only for specific experiments, but available to the general public for use in pesticides.
Yes, I believe that's correct.
And specifically, 2378 tetrachlorodibenzo-P-dioxin is the most toxic of all PCDDs.
Yes, that's correct.
Now, would you agree that it's likely that the 210 congeners that you mentioned have different modes of action in the body and that could affect and create toxicological effects in different manners?
Do you mean individual congeners act in different ways, or do you mean that as a group, dioxins can exhibit a number of different types of effects in the body? The latter is certainly true. I don't know if the former is true.
Now, when you came to this statement, you looked at the row data that we talked about in the De Bruin article, and we'll talk about a bit later, and you also looked at spawning and sediment data. So spawning, sediment data, as well as water quality data? Or are you making it solely on the basis of the row studies?
This is entirely based on the concentrations that were predicted to be in row. That's correct.
Okay. And you would agree then that on page 416 there's no entry for PCDDs. So if we turn to table 416, it wasn't actually measured in the sediment chemistry data for the Fraser Basin, and specifically the PCDDs.
We have not reported the results of measurements of 2378 TCDD in sediments in the Fraser River Basin.
Okay.
In this table, that's correct.
All right. And you'd also agree that dioxin-type chemicals have been decreasing in the environment since the 1970s?
Since the 1970s? No, I don't think I would agree with that. Since the 1990s, I would agree with that when we put the regulations on operating pulp mills in British Columbia. And I assume you're talking about not just the environment in general, but in British Columbia specifically. Since those regulations have been put in place, the releases of dioxins to the environment have decreased. The extent to which those concentrations have been reduced in sediments, I don't know that offhand. Again, these are highly persistent substances. We would expect that as the mass that is released into the environment decreases, we would also expect over time to see decreases in concentrations in sediments. But I don't know that for a fact. I haven't done that trend assessment.
Now, you used the De Bruin, the Kelly, and the Siska papers you evaluated them in your statement that you came to the conclusion on page 3 with respect to TCDDs?
Yes, that's correct.
Okay. And the Kelly paper in 2007 found that the PCDD toxic equivalents were at a level within the guidelines?
That should be table 5.20, is that correct?
Yeah, the reference that I'm looking at is page 70 of your report, second paragraph.
Sorry, table 523. Once again, De Bruin, we've adopted a toxicity threshold for TCDD toxic equivalents in salmon eggs that came out of a study conducted by John Giese and his cooperators. I think he was at Michigan State University at the time, and reported in De Bruin, and that is a level of 3 picograms per gram lipid in salmon roe. And I think what you're referring to is the data presented in table 5.2.3, which show results for early Stewart collected at various locations that range from 0.14 to 0.49 of picograms per gram lipid, and data for the Weaver Creek stock that range between 0.29 and 89 picograms per gram lipid. Is that correct?
No, actually, what I'm talking about is the Kelly paper, and the reference is on page 70.
Yeah, and the Kelly data are reported in this table 5.2.3.
Okay.
It's consistent with the information that you're pointing to on this particular page.
Okay, so then we have one study where the TCDDs were within guidelines. Is that correct?
They were lower than the toxicity thresholds, that's correct. That's not a formal guideline, it's simply a toxicity threshold reported in the literature. Those are different things. A guideline is promulgated by a level of government and is adopted as such and used in regulations and things like that. This is a toxicity threshold that came out of an individual study.
Now, the De Bruyn paper didn't actually sample Fraser River sockeye, is that correct?
They relied upon sockeye salmon that they collected in Alberni Inlet and in the rivers leading up to and beyond Great Central Lake.
Which is in Vancouver Island?
That's correct.
And no samples of any fish were from the Fraser River stocks?
I will double check that. Yes, I believe that to be true.
Now, De Bruyn tried to use mathematical modeling to prove that the TCDD toxic equivalents could be used. So he would use his samples from the Vancouver Island and try to extrapolate them to other stocks of fish based on their migration distance.
That's in part true. More, the model is based on mobilization of lipids during migration and how those lipids then get transferred to gonads of the organisms, and as that's happening, then how the contaminants concentrate that are already in the organism, but they concentrate in the salmon eggs and in the soma, in the muscle tissues also of the fish.
So basically, to summarize, De Bruyn took some samples pre-migration and post-migration and then compared the relative TCDD toxic equivalents and came up with a magnification factor, and then he tried to extrapolate it to other stocks.
Yeah, and the way that he extrapolated it to other stocks was he actually looked at changes in lipid content in those stocks through the migration pattern. So he didn't just simply say, here's my magnification pattern for the stocks on Vancouver Island. They developed a model that utilized their understanding of what had happened on Vancouver Island, but then relied upon data, actual measured data on lipid levels in actual salmon from 3 different stocks in the Fraser River.
Okay.
So it wasn't a direct extrapolation in the way that I think you're characterizing it, direct extrapolation of the magnification factor. It's actually using information on the lipid levels in those fish that are doing those migrations. And those were measured in those Fraser River stocks.
And the sample sizes were incredibly small. Would you agree with that?
What do you mean by incredibly small?
6 females on the pre-period and 2 females on the post-migration that were compared, so 6 and 2 animals in total?
Yeah, I believe those were the numbers.
And certainly that would not be enough to be statistically significant.
One would like to have more information if one was looking for statistical significance. But once again, this study wasn't conducted to demonstrate that levels of TCDD toxic equivalents were elevated in the row of Fraser River sockeye salmon. What it was done was to illustrate that they could be elevated, and that this is something that we need to look at more carefully to determine if this is a problem or not. So you need to keep in mind that the purpose of this was not to demonstrate statistical reliability of the results or statistical applicability of the results to the Fraser River. That wasn't the purpose. It was to demonstrate that there was a potential problem that needs to be investigated.
But certainly it couldn't be formed to to create the conclusion then that there was a problem with TCDDs?
I believe the way that I've characterized and used that information on our report is to indicate that the concentrations in Roe either exceeded, were at concentrations that either exceeded, how did I put it exactly? Either occurred or were likely to occur at concentrations in excess of that toxicity threshold. And so for me, the work that was done by De Bruin et al. Is convincing. It was a well-designed study, and it provides me with information that I need to be able to say, geez, you know, those predictions look pretty good to me. And this is a potential problem. And if we choose to ignore problems like this at address, we can, at our own peril, we can say it's not statistically significant. And I would agree that it's probably not statistically significant, but what it is important. And that's why we've focused on it in our report.
Now, in De Bruyn's results on the Great Central Lake, it showed, if you look at the lipid normalized values in the row, it was lower than 3 picograms per gram. And specifically, I'm looking to figure 6. And that would be the 2 bars. We've got the level of 3 picograms, and we've got coastal and GCL.
Yes, that's correct.
Okay. Now, if we turn to the other paper that you're looking at, the SISCA analysis, and you'd agree if you look at page 52 and the bottom chart, all of the samples, with the exception of Weaver sockeye, fall below the 3 picogram per gram of lipid.
Yes, that's correct.
And the Weaver sockeye, the error bar is such, or the error rate is such that the amount that it's over by 3 wouldn't actually be statistically significant.
I don't believe there's any evaluation of statistical significance at all here.
Okay.
All that shows you is what the error bar is.
And you'd agree that it falls within the error rate?
I don't know what you mean by that. I'm sorry.
Well, would you agree that when you have an error bar, it means that the value above and below it signifies the error of the measurements that are being taken?
Yes, I do. And what it also shows is that the mean concentration exceeded the toxicity threshold. So whether there was, and it shows, what it shows is that there's variability in the results. That's what the error bar is showing, is that there's some concentrations were lower, some concentrations were higher. But on average, the concentrations exceeded the toxicity threshold we're talking about.
On page 30 of your report, you cite a 1998 study by Sylvester.
Sorry, page 30?
That's right. In paragraph 2.
Yes.
He measured some effluents downstream of Anasis Island.
I'm sorry, could you refer to that again?
Sylvester. Got that?
Yeah, just sort of. I didn't hear the first part of your
Okay.
question. I'm a little hard of hearing, so I sometimes miss things.
Oh, I understand. I usually talk very softly too, so I'm sure I'm not helping. Would you agree that Sylvester measured some effluents downstream of Anasis Island?
Upstream and downstream.
Okay.
Not the effluents. What they measured was contaminants in the Fraser River, upstream and downstream of Anasis Island.
And this was in 1998.
That's correct. Well, the sampling wasn't in 1998. The may not have been in 98. The report was published in 1998. I've forgotten exactly what year they collected that data. I expect it was like a couple of years before that.
Okay. And chromium, copper, iron, and zinc and PCB levels exceeded water quality guidelines in Sylvester's report.
That's my recollection, yes.
But you would agree that based on Table 4.3 of your report at page T95, the 1998 findings are not consistent with your water table charts?
Sorry, what table?
It's page T93, and it's Table 4.3.
Okay, and sorry, your specific comment was what?
You would agree that the Sylvester findings were not consistent with your findings on your water table?
Can you be more specific about not consistent in what way do you mean?
Okay, and specifically, iron, cobalt, and chromium were within the guidelines on page 93 of your report. So that would be Table 4.2.
Yeah, so I think the point that you're getting at is that the data that were evaluated in Table 4.3 did not include the results from Sylvester, and that's true. That we did not have those data electronically, and so that's why I described them in the text rather than trying to incorporate them into the table specifically.
And you would agree, though, that the measurements in the table, they'll fall within the guidelines?
Sorry, for...
Specifically for iron, cobalt, and chromium.
Iron, cobalt, and chromium. Well, I see a max level here of chromium of 44 microgram per liter. The Canadian Water Quality Guideline there's two Canadian Water Quality Guidelines for chromium. One is for hexavalent chromium, one is for trivalent chromium. The trivalent chromium Water Quality Guideline is 8, and the hexavalent is 1. And so this concentration would exceed both of those levels. I've forgotten exactly what the Water Quality Guideline is for iron, and I think if we probably look back, we can figure that out. Iron is 21,200. Maximum is lower than that, so that's correct. And then cobalt, there was no Water Quality Guideline for cobalt identified here in our study.
Okay, when I'm looking at your chromium total, I have number 4.48 as the median, and the selected TSC on page 93 is 43.4. Is that?
That is correct. So what we've done there is, sorry, on page, I was looking at the wrong page, I'm sorry.
Okay, so you'd agree then with my question?
Well, I can't agree with you yet because I have to go to the right page and then look at the results. So you're looking at table...
And you should be looking at the errata version as well, since this is one of the pages that you had changed, but I think it was, the numbers were changed to micro from milligrams.
Okay, so just, let's go back a step. So we're looking at table 4.3, is that correct?
That's right.
Okay, so that's surface water chemistry data, correct?
Right.
And then, so what we need to compare that to is the data in table 4.1, which is the toxicity screening values for surface water, correct?
Okay.
So cobalt, on this page, let's just make sure we go to that page first, shall we? That's T90. So from this page, it's what you'll see is a chromium level of 1.0. Is that correct? It's also on the screen now.
Okay. All right, so you're right at the level. Okay. All right, so we'll move on.
How much longer are you going to be?
I've still got 2 pages because he was a lot longer than I thought, but I can maybe speed it up and cut most of it out.
Well, why don't we take the break and we'll see if we can do that.
Here, we'll now recess for 15 minutes.